Wait, you really are going?
I'm going.
Are you getting paid?
I'm getting supervising hours from my administrative program.
That's good. Just make sure to close your eyes.
So, regardless of what class you were in at the beginning of the year, every secondary 3 class went through this in the first unit. Do you remember having to subtract here and subtract here to figure out what the degree of the polynomial? Does that sound familiar? This ties into the lesson. This is not just review for review's sake. Ties into the lesson. So, hold on. I'm going to start recording with this little Bluetooth thing.
Oh, that's so cool.
So you can hear my, because when I stand over there, you can't hear my voice.
Why do you say that?
But when I'm drawing on the board. Ta-da! Test. Test. All right, it's working. So, it's been a while, huh? What's 5 minus 65?
Negative 60.
Negative 60. What's... All right, you guys got to start being careful now. What's negative 5?
Negative 10.
Negative 10. What's negative 1 minus negative 5?
4.
Good. 5 minus negative 1?
6.
Is 6. 25 minus 5?
20.
And 95 minus 25?
70.
Are these, what does this tell you?
Tells you that they're not cubic. Or, yeah.
It's not degree 1. It's not degree 1. Okay? So, what's negative 10 minus negative 60?
50. 14.
4 minus negative 10 is 14. 6 minus 4
2.
is 2. 20 minus 6
14.
and 70 minus 20.
20.
What does that tell you?
Almost. Yeah, so it's not
degree 2.
Yeah. No,
Degree 2 would be a parabola.
It's almost like it's kind of like 50 given.
Now I have to check these differences. 14 minus 50.
36.
2 minus 14.
Negative 12.
14 minus 2. 15 minus 14.
36.
What does that tell you?
No, third.
It's not a third degree. It's not cubic. Well, what's negative 12?
24.
Minus negative 36, that's 24. 12 minus negative 12. Uh-oh. 36 minus 12.
24. Fourth degree.
It took 4 differences for the numbers to become exactly the same. That means it is
Fourth degree.
4th degree. This is what you guys did way back when,
Last year.
a couple of months ago.
Really?
This is this year. It's 4th degree. Okay? Now that you know the degree, and we don't have time for this, but do you remember when we had our calculators, you had to go to the list, you had to type them in a list?
Yeah.
Remember that? And then you had to tell your calculator to come up with an equation?
That's terrible.
Okay? So now that you know it's 4th degree, you can tell your calculator to come up with an equation for it. And you're thinking, well, that's stupid. Why do that? Some of the problems you had on Unit 1's test, you had to make predictions. You probably don't remember, but on the last page of Unit 1, you had real-life problems like that dealt with data from censuses and things like that. This is only a sampling of the data. If you had an equation for this, you could make predictions way into the future, or you could see how it behaved years ago in the past. Remember that? That's called modeling. That just means you get an equation. We don't have time for this one. You would have done the same thing, just find the degree. Here's a different table, though. So draw these numbers. Write them down.
Is that 192?
192 there at the end, yeah. So you have 1, 3, 2, 6, 3, 12, 4, 24.
Did you teach it in the school this year?
5, 48. Hey, I gotta kind of pick this up. You ready? 6 minus 3, go.
3.
12 minus 6. 24 minus 12. 48 minus 24.
4.4.
96 minus 48.
48.
And 192 minus. I want you to consider these numbers in this column and compare them to the numbers in this column.
Man, they're the same. You just took off the last number.
Well, does this tell us that it's a first degree?
No.
Not first degree. So what if we tried this difference? 6 minus 3? 12 minus 6?
It's going to be linear, right?
24 minus 12? 48 minus 24? And 96 minus 48?
Isn't it just linear?
It'll be if the first differences are the same as linear. First differences aren't the same. Second differences aren't the same.
4. They kind of sharpen the last one.
Well, they're not all the exact same number.
Oh.
They have to all, like this one here, they were all the exact same number.
Oh, okay. So
That means it's fourth degree.
So that's like.
It's not first degree. It's not second degree.
Oh, you're right.
What if I went to the third degree? What do you think I would find?
3,
6, 12, 24. What if I went to the fourth degree?
6, 12. It's the 6th degree.
If I had an infinitely long list of numbers and then I took all the differences out to infinity, what would all of the differences be? Wouldn't they all be 3, 6, 12, 24, 3, 6, 12, 24, 3, 6, 12, 24?
Yeah.
You guys see a little bit of a difference then between this type of a pattern and what will happen out here? These are polynomials. Polynomials, eventually you can get down to a difference that's the same number. Eventually. Might take a while. Okay, I want to make sure we're clear on this. You guys listening? If we went out as many differences as we could, would we ever get to where those differences are the exact same number? No. Because this is not a polynomial. Okay? What did I call it? Right at the beginning of the lesson, that money that doubled every time?
Exponential. That's what I
Alright. This is an exponential function. It doesn't have a degree.
That's how they take it down to one number.
Yeah, if it ends at one number, is that degree?
Well, then it's still
That's what
exponential.
the book said in polynomials, if it's a polynomial, not exponential. Because you can always just extend a table and have more numbers. I want to make sure we're clear on the difference here. With a polynomial, how do you know its degree? With a polynomial, how do you know its degree? When the differences become the same number, right? And how many differences it took is that degree. Or you can just look at the equation. What if I said the equation was p of x equals x to the fourth plus blah, 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 blah. What's the degree there? Obviously, fourth. That would be fourth degree. So either you have a table, you find the differences, or you just look at the equation. Exponentials don't have degrees, okay? Because you're never going to get to the same difference. Out here. So write that down.
You'll never be able to find the degree because these differences never change. It's always 3, 6, 12, 24, then 3, 6, 12, 24.
So does it have a degree? Like you can't find it, or does it?
Doesn't have a degree, no. This is what exponential functions look like. Y equals a times b to the x. Y equals a times b to the x. Biggest key here, you guys, is the variable is in the exponent. That's how you can tell whether something is exponential. It's not just because it has an exponent. A lot of things have exponents. If the exponent is a variable, then it's exponential. That means it's going to grow real fast. Like that money problem we took a look at. So it's going to seem easy, but this is how your homework kind of starts. It's going to give you a bunch of ones to look at. You've got to pick out the one that's exponential. So let me just erase. Remember that song from Sesame? Do you guys ever watch Sesame Street?
Yeah.
One of these things is not like the other. Remember that song? I remember that song.
Did they have Sesame Street when you were a kid?
Yeah.
What? Oh, back in the Stone Age?
Yeah.
Wow. Stone Age?
When I was watching Sesame Street, they still had Cookie Monster.
I thought they had like...
I think they brought him back, but a couple of years ago they experimented with Veggie Monster.
Was it like black?
It was stupid.
Was it like black and white? No.
No. But they brought back the Cookie Monster. Which one's exponential?
Only one of you gives the answer. With such an easy problem, only one of you knows. That's pitifully good.
I know.
Pitiful!
I know. That's
The third one. Third one's exponential. Because it has an exponent? Because the variable, they all have exponents, but only one of them is exponential. It's exponential because it has a variable exponent. These top two, if the exponent is a whole number, those are called polynomials. Yep. And the exponent tells you this is a degree 2, that's degree 4. The reason, Abby, to go back to your question, the reason exponentials don't have a degree is because we don't know what the exponent is. It's always changing, x is always changing. This one isn't a polynomial because the exponent is not a whole number. Who took secondary 2 last year?
honors.
Is this ringing a bell? A power of 1/2 is just a square root.
Yeah.
Does that sound familiar? That's all that is. Y equals 2 times the square root of x. You.
First thing you're going to do on your homework is identify if it's exponential. Can you identify if it's exponential? Yes or no? Only 2 of you answered. Can you identify if it's exponential?
Yes.
Okay. The second thing you're going to have to do on your homework is make a graph by making a table.
There we go. 3dx. You guys don't have any tables. It's not that hard to make a table.
You can choose your x values here. I'm going to choose 1, 2, 3.
What's 3 to the first power? 3 to the second power? Oh, say that again. Yeah. 3 to the third power? 30, 20, what? 3 times 3 times 3.
Yes, 27.
I'm going to throw you up here.
0.
1.
3. 1.
1.
To the power of 0. Why is it 1?
Anything to a power of 0
For some reason.
is 1.
No, that wasn't possible because if you have 0, 3, then it should be 0. You just imagine that.
Alright.
If you think about it, it's about jokes.
Is that because mathematicians decided to be that way?
Do you guys agree with this?
That's 3 to the power of 1.
You guys agree with that?
Sure, yeah. Divide 1 by 2.
You guys learned this last year. I'm sure you forgot, or maybe even in secondary 1.
Order of operations.
But when you're dividing terms with the same base, don't you subtract the exponents? Does that sound familiar? If you're dividing terms with the same base, you subtract the exponents. So 3 to the 2 minus 2 is just 3 squared over 3 squared. And what is 3 squared over 3 squared?
1. What?
could have done this with any number, 5 minus 5 or 10 minus 10. Anything to a power of 0 is always equal to 1 because it's just something divided by itself.
It's really confusing.
Clear on that?
Yeah. But it's not weird though, because if you have 0 and 3, it's not going to be more. Just because of that. Like, just by looking at that one.
It's kind of weird, isn't it? Math is weird.
Math is so fun. It makes sense. It's just.
Okay, so anyway, can we at least... Here's a better proof. The calculator says so. Oh, so it's got to be true. There we go. Ooh, what about this one? Be careful before you blurt out an answer. Three to the negative 1.
That's 3.
Do this. Type it in your calculator.
Fine.
3 to the negative 1.
You love him? Why don't you marry him?
It's 1/3.
1/3.
I don't know who you had last year, but they may have taught you this goofy little phrase. A negative exponent hops the line and changes. Does that sound familiar?
No.
A negative exponent hops the line and changes the sign. So 3 to the negative 1 is 1 over 3 to the positive 1. Not familiar to anybody?
My teacher was boring last year.
Shut your mouth.
Fine.
What's pretty boring?
So what about 3 to the negative 2 then? Be 1 over 3 squared, which is 1/9. This is all stuff you should have learned previously. But anyway, we have enough points to draw a graph. Draw your graph. Plot the points. You have 0, 1. You have 1, 3. You have 2, 9. Negative 1, negative 1/3. Negative 2, 1/9. So if you just connect the points that we have, we have that kind of graph. I need you guys to look real closely at my graph. You ready? Put your pens down for a second. This point right here, is it above, below, or on top of the x-axis? That point right there. What if I went to negative 3? Wouldn't that be 3 to the negative 3, which is 1 over 3 cubed, which is 127? So at negative 3, it'd be 127. Is that above, below, or right on top of the x-axis? What if I went out to negative 4? That'd be 1 over 81. That'd be above, right? But aren't I getting close to the x-axis? Am I ever actually going to get right on top of that x-axis or cross through it? Because this graph doesn't just start here, it continues on forever and ever in this direction, but it just gets closer and closer to the x-axis without actually touching the x-axis. It just gets smaller and smaller fractions. You have 1/3, then 1/9, then 1/27, and then 1/81, and so on and so on. And this continues to go up and up and up.
Can you stare at better to it for confidence?
Okay. So, okay. Think about that penny problem. The first couple of days, was it growing very fast? You had 1 penny, then 2 pennies, then 4 pennies, then 8 pennies. That's kind of like this part of the graph. It's not growing very rapidly, is it?
No.
What happened after just about 2 weeks? What happened?
Bad.
After a couple of weeks, that money started to really grow, really rapidly.
Yeah.
That's exponential type growth. It's not real big at first, starts to grow real rapidly.
I like this one.
So, write this equation down. 1/3 to the power of x. One third to a power of x. Ooh. True or false? You guys ready? This is a 50-50 shot if you're guessing. You got 50-50. True or false? This equation right here that I'm circling is exponential.
True.
Why is it true? The variable is an exponent, right? The base here is a bit different. It's a base of 1/3, but the variable is still an exponent. So yes, it is true. This is exponential. All right, I'm tired of standing. Mason, hop up there. Take the pen.
Come on, Mace.
You're going to fill in the y column for us. You guys need to help us all out, though. If you plug in a 0 for x,
It's 1.
It's 1.
And then 1 divided by 3.
if you plug in a 1 for x, you're going to get 1/3 to the first power, which is 1/3. Ooh, tough one. What if you plug in a 2? You get 1/9. 1/3 squared means 1/3 times 1/3, which is 1/9.
That's just negative 1 over
1/3 to the negative 1
negative 1 over 3.
is 3. Positive 3. Okay, check it out. You guys listening carefully? I need you to listen. If you have a fraction to a negative exponent, you flip the fraction upside down and change it to a positive exponent. So 1/3 to the negative 1 is the same as 3 to the positive 1, which is 3. All right, plug in a negative 2. You would get 9. Thank you. You can sit down now. Tired of looking at that ugly jacket.
Hey, so neat. Oh, so neat. Do I get up there?
What do you have, a nice looking Utah jacket on here? Nobody?
Can I get up there?
You don't have a Utah jacket.
I have an American Eagle, please.
You drive a graphic. Okay, drive right.
You play instrument?
I do. The radio. No, I play the piano.
I wanted you.
How much?
Yeah, like pretty good.
I had lessons for like 13 years.
Whoa. That'd be terrible.
It was awesome. I don't know why I quit.
You can still play pretty good, right? You can play well. Yeah.
So we have 0, 1.
Well, first of all, didn't we decide this was exponential? So shouldn't this graph look an awful lot like the graph we just graphed? So we have 1, 1/3, we have 2, 1/9, we have negative 1, 3, negative 2, 9. Does this look exactly like the graph we just graphed? Is it similar, yes or no?
Similar, yes.
Okay. There's 2 types of exponentials you guys are going to have to identify in your homework. You ready? You listening?
Yeah.
It's not just knowing whether it's exponential. Was this exponential?
Yeah.
Sure. But there's 2 different types. This one here is called exponential decay. Exponential decay. You'd see it in a science class if you were studying radioactive material. Have you heard of half-lives, right?
Yeah.
When do you study that? Chemistry? Physics? Chemistry? Half-lives, it's just exponential decay. You start out with a lot, and it decreases by half every time, which is kind of what's going on here. Here it's decreasing by 1/3 every time, but it's the same thing as exponential decay. You guys are pretty clever. If this is called exponential decay because it's shrinking, what do you think this one's called? Exponential growth. Exponential. You probably also studied this in chemistry. How does bacteria grow?
It multiplies by like as fast as rabbits do. Probably like double.
1 bacteria becomes
2.
2, then become 4, and then 8. That's exponential growth. And rabbits apparently grow that way, right?
Rabbits grow.
And
Insane.
Utah County population grows like that. Anyway, I wasn't going to say anything.
Kind of is, isn't it? Yeah. You need books. Get them. Get them!
Yeah, you stay.
Volume 1 now. We have to backtrack, dang it. We skipped over chapter 5. Because I wanted to do trigonometry before you guys took the ACT.
Fine then.
I think it might have helped. I hope it helped. While we're on the subject, though, you guys ought to plan on taking that ACT at least twice more. At least. Yeah, you never take it just once.
Don't you have to pay for it?
It's your future.
Yeah, and how much you pay for it?
Go babysit or something. I don't know. You guys, the whole argument of, well, my parents never went to college, they're doing okay. That kind of stuff doesn't happen anymore in this modern age. You've got to go to college. You really do.
Yeah.
Yeah? Most of the jobs you guys are going to get don't even exist yet. Technology is changing so quickly and so rapidly that there's going to be new jobs created we don't even know about. And they're going to require an advanced degree. Okay? And here's the thing. The rest of the world isn't slowing down. If we're too stupid in America to fill jobs, guess where they're going to get them from? China, India, Japan. It's a global market. They don't have to live in the United States to work here. You understand what I'm saying? Okay. Go to college. Okay. But that ACT is your ticket. It's got to be a good score to get into a good college. Anywho, I'm off the subject. Go to page 300 and is it 11?
That's pretty lucky.
Ooh, I like that band. 311. 311. Actually, it's not 3. It's like 312.
Were you an ACT proctor there?
Yeah. Did you have to kick anybody out?
Not in my class.
No, it's 313. I keep telling you wrong, sorry. 313. Look at 313. Right at the very top of 313. You see how it says problem 2 got it? I want you to do part A and B. They're asking you whether it's growth or decay. Wait. Before you do, sorry, jumped the gun. Piece of information you need.
Does that say so?
So.
I thought that was a 5.
Isn't it so a deer or female deer?
No.
I'm just kidding.
No.
Homer Simpson made up his own song for that. Have you guys heard that one? Never heard it?
Let's listen to it.
It's not really school appropriate.
Who cares?
High school probably.
You ever heard of Homer Simpson's version of that song?
No. Oh, pretty sure.
Well, this is Utah County. You guys are forbidden to watch The Simpsons, aren't you?
Hey, no, I go.
Wasn't allowed to.
I'm annoyed by it.
My family was allowed to watch SpongeBob.
Huh.
Okay, guys. How do you know whether it's growth or decay? It depends on the base of the equation. And by base, I mean the thing connected to the exponent. This is not the base right here. That's just the coefficient. It's the base of the exponent. Okay? If the base is larger than 1, you know automatically it's growth. If the base is between 0 and 1, you know it's decay. You don't have to look at the graph. All you got to have is the equation. So, now do problem 2, part A, and part B. Not writing in the books.
So we don't have to like do all of them.
You don't have to graph it.
I'll draw the minutes.
All you got to do is identify which one's growth, which one's decay.
Oh, it already says.
It does not.
Are you talking about right here? Problem 2, you got it. Oh, that's easy. It's decay. You know how it has decay. That is
That is true.
You are correct.
Well, if the decimal's smaller than 1.
Oh, yeah, sorry.
Yeah. Was it a real hard choice? You didn't read all the directions, though. There was one thing we left off. Okay. You might want to write this in your notes, because apparently every student on the planet has forgotten this. How do you find a y-intercept?
Rise over run. Wait. No, wait, sorry. The y-intercept. It's where the x crosses the y-axis.
Okay, check it out, you guys. Is this a y-intercept, yes or no? Yes or no? Go ahead.
Yeah.
What's the x value right there?
1.
0, 1.
It's 1.
X value.
Oh, that's 0. 0, 0, 0.
Okay, check out this graph. Is this a y-intercept, yes or no? Yes. What's the x value?
0.
What if the y-intercept were down here? What's the x value?
0.
What if we were way up here?
0.
So, to find the y-intercept of any graph, how do you do it?
You plug 0.
You plug 0 in for. So to do that also, not only to identify if it's growth or decay, I want you to tell me the y-intercept. By plugging in a 0 for x. And it's something that you ought to be able to do in your head. For these simple ones at least.
It's just y equals 11. Right? That's I'm doing good today.
You are doing
I'm trying,
pretty well.
I'm trying to get some answers.
Is that what you guys got for part A?
I got it.
Growth.
Yeah.
What was the y-intercept? 0, 3. Just so we're clear. If you plug in a 0 for x, 4 to the 0 power. 1 times 3? It's 3. For part B, you got
Decay. Because this is the base right here. The base is between 0 and 1, so yeah, it's decay. Y-intercept is 0, 11.
What is it if it's less than 0?
Ooh, that's a good question. Did you guys hear that?
What is it if it's less than 0?
If the base, so you're talking about the thing inside the parenthesis, right? If it's less than 0, it's not exponential. Weird, huh? Check it out. That's actually kind of a cool.
Check it out. Negative 2 to the x. Is the base less than 1, or less than 0?
Yeah.
Is the variable an exponent?
Yeah.
But this is not exponential. Here's why. If we graph this, what's negative 2 to the first power? Or sorry, what's negative 2 to the 0 power?
0. Oh, 1.
What's negative 2 to the first power?
Negative 2.
So we'd have 1 comma negative 2, right? But what's negative 2 squared?
4.
So now we'd have 2 comma 4. What's negative 2 to the third power? So negative 8 will be down here. Negative 2 to the fourth power?
16. Oh, so it's the...
So it just keeps going on. You see how it's not exponential. The base can't be negative. Okay, does that answer your question? The base has to be greater than 0.
That's crazy.
I know, I kind of got up there, but I missed a couple of dots. You guys get the point. Stand up for a second. I told you to.
So I watched the rest of that last video.
Where'd you find it?
I don't know if it's legal, but I watched it on YouTube.
Yeah, if it's on there.
Yeah. I watch a lot of movies on YouTube. Like, you just type it.
We never finished that movie?
No.
We never did, and it's driving me crazy. How do you say
Oh, it's so sad.
He gets run over by a truck.
He gets so sad.
You remember how that lady comes with the truck all the time?
No.
You know that it was a couple months ago about the guy that has Tourette's and he teaches a class or he wants to become a teacher.
Okay, don't tell us this last watch.
Did you see the part where he becomes a teacher? Well, so you know that lady that comes in with the big rig, the truck. She comes in every now and again.
The one that you showed us about the map, like the different
Yeah.
Oh, that makes sense.
The nice lady that has the, well, she comes in one day with her big truck and she doesn't see the guy there and she runs over him. Really sad story. That's not how it ends. That's not how it ends. Wouldn't that be a weird ending though? And it ended up killing him. Just like you guys are gonna end up killing me. It. Yes, turtle unicorn.
They're gonna accidentally measure out as like
Okay, we gotta finish up. We have 8 minutes, you guys. Stay with me. Sit your butt down. We're gonna do it. We're gonna model. You guys ever wanted to be a model? Modeling mathematically means you create an equation that fits a situation.
Can I just go around the board?
No. Come on, you guys. Write it.
What am I writing?
That.
Which part?
2 plus 3 plus 4 plus 5.
I want you to write the 4th letter on the 6th line, and that's it. No, write the whole dang thing.
For a second, I thought that said
No,
We're almost done. Yes, remember back in Unit 1 how to find a model for a polynomial you had to type it into your list. Then you had to go to that regression, like quadratic regression or cubic regression. Does that sound familiar? And your calculator had to tell you what the model was. With exponentials, it's so much easier.
I thought the whole thing felt looking at it. It's a mess.
Well, how's that going to help you?
Well, I was seeing if I could do it like accurately.
This is going to be your formula for all your exponential models in this section.
Yeah, okay. That makes sense.
Cool, huh? What's that? There's a 1. 1 plus or minus r to a power of t.
Somebody hacked me and was posting that stuff, so I had to delete it. It's bad. Someone hacked my Twitter and was posting bad stuff. Yeah, somebody hacked me. I'm sorry. I just felt so bad, even though it wasn't my fault.
Wait, is that a 1 or an L?
This is a 1 plus or minus r to the power of t.
Someone who has insane attachment.
Now, you guys aren't going to use the plus and the minus at the same time. It depends on the situation. If it's something that's growing over time, like money in a bank, that's plus. If it's something that's decreasing over time, like the value of a new computer, I don't know. Let's say you buy a computer for $3,000, but it depreciates. You guys understand the word depreciate?
Yeah.
It depreciates in value by 2% per year. That's decreasing in value, right?
Yep.
So then you would do 1 minus r, because it's getting smaller. You see the difference? R is the rate of growth or the rate of decay. So if your money is growing at 6% per year, then it would be 1 plus 0.06, because 6% is 0.06. Your initial amount, that's what goes here.
Wouldn't it be 1.606?
It would be 1 plus 0.06, which is 1.06.
Oh.
Yeah. So I'm going to describe a situation for you. I want you guys to see if you can write the equation for it, just based off my verbal description. You ready? You invest $500. for 10 years, and the annual interest rate is 5%. You invest $500 for 10 years, and the annual interest rate is 5%. How much money would you have after 10 years?
500 divided by
Now let's go through it. What's A in this situation?
500.
The little a, the little a right here.
Oh,
That's 500, right?
Yeah.
The big A, that's the amount after so many years, but the little a is 500. What's your R?
10 years.
0.05,
Oh, rate.
because it's your rate. Now, are you going to do 1 plus 0.05 or 1 minus 0.05? Plus, because shouldn't your money be growing over time? So you're going to do 1 plus 0.05. And what's your value of T? 10. Okay?
Wait, I said the other two too.
So, there we go. Invest $500. It pays 5%. How much after 10 years? So here's what your formula would look like. That was a different class.
So you would say the amount after 10 years is equal to, what was the initial amount? 500.
1 plus 0.15.
What you gotta do is plug this into your calculator. 500, parentheses, 1 plus 0.05, close parentheses, raise it to the 10th power, hit enter. It's so easy that most of you can do. What's that? 5%, that's pretty good interest rate.
Really? How is that normal?
No, that's a little high. Now this is assuming that you don't make any future deposits and you don't make any withdrawals. You just leave it in there for 10 years. And it's also assuming the interest rate stays the same for 10 years. But if that's the case, how much money are we going to have? 800 and... That's nice. You got money without even doing anything. Here's a question. How much interest was there? Come on, you start with 500, get it with 800. 14, how much interest was earned? $314.44. So you have a few examples in your homework where you have to create a model. Was this really that hard to do?
No.
Every single model you create is going to follow this pattern. Your initial amount goes here. How do you know whether it's plus or minus? If it's growing or shrinking. Okay? The value of time is your exponent. So modeling with exponentials is pretty easy.
It's an online homework assignment, you guys, so go on your Math Excel. It's only like 10 problems. And 4 or 5 of them, you just have to look and say whether it's growth or decay. How long does that take you? 10 seconds, maybe? Okay, so this homework isn't a big homework assignment. Get on and do it, get her done.
Yes, coach.